And the aim of this presentation is mostly for you to see a different perspective of what you're doing, a different perspective of a different flavor of work. So yes, I'm doing machine learning. Yes, I come from the Technical University of Crete, and all my background is on electronic and computer engineering, and with a very big focus on machine learning. But what is really inspiring for me is to see how what we can do can apply, can embed itself in society, and how we can help more people, or even one, with what we know how to do. And perhaps parts of this presentation will seem naive to you, will seem not as advanced and not as sophisticated, but you will be surprised of the models that are being applied and are being used in everyday life and in everyday decision-making applications all over the world, and have really, really basic biases or shortcomings or blind spots that we can improve. So this is mostly for you to see how you can contribute in this area of humanitarian response, how you can help the community with what you know how to do best. So a little bit on vulnerability. What is the notion of vulnerability? And it's a very wide one, right? So each and every one of us is vulnerable in a totally different way, because it depends on our personal characteristics. It depends on the access that we have to information, and it may be that simply, being exposed to misinformation is a form of our own vulnerability, or the fact that the loan you may ask may be determined by an algorithm or not. Here I'm going to focus on extreme vulnerability, of people that don't have access to basic goods like education. So I'm not going to talk about misinformation on regarding the COVID vaccine, but I'm going to talk about children that have no access to vaccines and they die. So in this extreme area of work, we have really big challenges to face, and most of them you probably imagine, like biases in every single step of the pipeline, but also our own biases. Because, one of the aspects that is not so evident sometimes is that we as engineers, we want to do cool stuff, and we want to show that we know how to do an amazing neural network. And, we can put up a huge pipeline, but then what people in the field really need, it may be simple. And what is the most important thing in this domain is to be able to explain what the model does. So each and every one of these steps of the process can be an entire class, right? So I'm not going to go very deep into all the aspects and all the problems and all the challenges that you may face in every step of the way. But the most important ones that I want to highlight are sampling, for example, and the coverage of data. So when you're making a machine learning model for the United States of, I don't know, and you're using mobile phone data, you have an amazing coverage. When you move this thing to Mali, the data are really sparse. And when you want to transfer a model that you have learned in a data-rich country to a country that nothing exists because there are no apps, there is no internet connectivity at times, and so on, you have a totally different set and magnitude of issues, right? The other interesting aspect of what we're doing is that we're working with vulnerable populations. So sometimes, most of the times, what we do as pre-processing in a classic exercise, in a classic machine learning problem, is to take out exactly these populations, because we're filtering our data in order, to have the perfect sample to train our model. And in my case, these are the people that I care about, the outliers of your machine learning models. So there's a lot of systematic missing of people, like imagine undocumented migrants. There is a lot of sensitive attributes. So, you make a very basic classifier. We will see examples of this. I will show aspects of this through case studies, so that you see a little bit how this translate into real life issues. We are facing issues of awareness. So sometimes we don't know. Sometimes we haven't thought about biases that may exist in the models. And other times we have data that come from different sources. So different actors collect data, more or less of the same topic, more or less of the same format, and then you have to put them together. But perhaps the questions are different, perhaps the structure is different, and then the harmonization of this data is a huge, can bring in a lot of errors in your pipeline. Now, the choice of the model, another huge choice, depends on the data that you have, depends on the quantity, on the quality of what you're trying to predict. The biggest issue here is the explainability, and this is usually what is going to be the determining factor of the models that we're choosing. How we train our models? Well, we have reached this part of the pipeline with sparse data, with missing labels, with missing. So to train the model, of course, you're dealing with huge class imbalances and rare events. Fortunately for humanity, unfortunate for my for my training models, what we deal with and what we're trying to learn often occurs very rarely. And the other thing that is very important to keep in mind always is that accuracy is not always what we're going for here. So the usual, the first parts of the pipelines are easier to be aware of, right? They're easier to have an eye and say, okay, I have to be careful on the choice of the data, on the coverage, on the representativity. But then when it comes to the model tuning, it's really easy to make models that overfit your data, also because the ground truth is really bad. Also because the ground truth often comes from sources that are put up in emergencies. So people just document, imagine, I don't know, war situations. There is documentation, but the urgency and the speed in which these problems are documented is so fast that the documents that you get are unstructured, are all over the place, may exist in emails, may exist. I mean, it doesn't necessarily. It's not necessarily. It's never going to be a clean database that you get for a school project, right? So the validation of the models themselves becomes really tricky. And finally, it comes to deployment, because my work doesn't stop at publishing a paper. My work doesn't stop at creating a model that with very good accuracy and handing it over to someone else. But this model gets deployed. And what this means is that people's lives depend on it, more or less, maybe affected more or less, but still there is a huge responsibility that comes with it. So transparency, sustainability, all these concepts, also the responsibility of who gets to run your model and how much he understands about your model and what are the shortcomings of it and how this can be reutilized in other, the control that we have in reutilizing these models in other scenarios. For example, I build a model for, I don't know, a typhoon in the Philippines, and then people say, okay, we can plug it in another country and it will work the same. More or less, so you have to educate people that are going to reutilize your models. Now, I have started with only problems, right? And this is what is interesting to me, the fact that there is always a new challenge, there is always something something that I haven't seen before. And this is the beauty of it, right? That most of my students deal with frustration because they have to struggle with all these different issues. It's not just one problem to solve, it can be anything. So this is a toy example that is a real life case but never got deployed. So it's a nice toy example to see the notion of fairness in machine learning models, right? So what happened is many years ago, an Italian NGO came to us, and their purpose was to give educational information to unemployed young people. So what they wanted to do, they wanted to have a Facebook application. This was deployed in Italy. And basically this application, I'm talking more or less when the Facebook advertising platform was starting to exist. What this application does is basically that it's deploying surveys, quizzes, and so on. And what we get out of this is people's likes on pages. And we also had socio-demographic information that they would provide. And so the question was, okay, if someone new comes in this application, can I infer what is their employment status? Because not necessarily they fill in all the information, right? So for the people that we knew what their employment status was, we saw a little bit the representativity of the Italian census in our sample population, and more or less follows the census of Italy. And the most important thing is that although we have more students than the Italian census, the unemployment percentage was the same, which is important for what we want to do. And it was more or less equally distributed between males and females. Now, of course, usual toy case study of machine learning, you have your features, you do your XGBoost, and then you try to predict the employment status. And we have a very good accuracy, a ROC score. Now, disclaimer, this is a very good ROC score for people that do computational social sciences. If you go to telecommunications, people will have a heart attack. But for us, it's an amazing result, right? It's a model that you say, okay, it works, we move on. And this is what they wanted to do, but then I said, no, wait, first we have to see how this model takes decisions. What are the important features of that? Now, I don't know if you're familiar with SHAP or not. Yes, no? No? Oh, no. Okay, so I will go through the details of SHAP in a while. Okay, so first thing, just a very brief introduction to SHAP. SHAP is it's a method based on game theory, and basically the idea behind its value is that in a game you have multiple players, and the Shapley value will give you how much each and every player contributes to the final result. So let's say that we all, 4 people win the competition. We have 10,000 euros as a reward. How do you divide the award? You divide it by 4. Okay, but I may say, yeah, but I worked more and Stefanos worked less. Why should we get the same money? So SHAP was developed by Lloyd Shapley, a mathematician back in the day. And basically the whole idea is that it checks all the combinations of players and what is the score that they could achieve together or alone or in all the different combinations, and it gives you a value of how much this individual player has contributed to the game, right? This transposed in machine learning, it gives you how much each feature contributes to the outcome of the model, right? And it has very nice properties like additivity. So, if you sum all the contributions, you get the final score. It has a very important value attribute of giving you scores that are comparable across models. So if I want to compare a linear regression with an XGBoost and with a neural network, the value that I'm going to get is comparable across models. It has limitations as well. So it's not, if you have causal models, there is no, the limitation is that you cannot get causal effects with Shapley values, right? Anyway, so this is a very brief explanation of it, how to read it. From one side, we have all the features. They're ranked in terms of importance according to their Shapley values, as I said before. And then you have colorful dots. So the color of a dot depends on whether it's associated with a low value of the feature or a high value of the feature. So in this case, purple dot for age means that you're young. Green dot for age means that you're older, right? And where you stand in this axis is how much you contribute to the output of the model. So if you're in the 0 line, you don't contribute. If you're higher, lower, you contribute to one or the other side. So I don't know. For example, if you see gender, you have purple. Here I have encoded females with 0 and males with 1. You see that, if you're a female, you're more likely unemployed because you're on the side of the low side of the model. Anyway, so the most important information of this is a very nice tool, and you can use it in your projects to show, what are the important features of each classifier that you're using. But what I wanted to show you here is that the most predictive features are demographics. And this is okay for the people that are that are doing advertisement, for example, because sociodemographics is the number one tool they have to make profiling, for example. But in this kind of problem, in this type of task, is a problem because I don't want my model to give you information according to your gender or your age. I want it to be agnostic of that because I don't want to enforce any marginalization that may already exist in society, right? So what people usually do are many approaches. So one are the non-quantitative ones. So you just explore, you say, okay, I'm going to spend more time to understand my model. I'm going to try to use more explainable AI, or I'm not going to use a model at all because this is not something that I can solve. Or they try to solve it, and this is more what we can contribute to, right? So the quantitative approaches are three. The first one is pre-processing, and it doesn't work. So what is, most of the times it doesn't work. So what is pre-processing based on is basically based on hiding information from the model. So I'm going to take out the sociodemographic, and this is what is generally called fairness through awareness, right? So you take out the features that you don't want to be part of your models. Surprise, surprise. So I bet that people that have liked on Facebook health and beauty and clothing are females, and people that have liked politicians, car and football players are males, right? So the whole thing is that even though I'm not showing to my model the gender and of the participants, these things are so embedded in our everyday behavior that there are so many proxy variables that can give this out, right? And it can happen in many. This is a toy example, but it can happen in real applications. For example, imagine, I don't know, cities with social segregation. You have the rich people living in one side of the city and the poor people living in one side of the city. You may not use their income as a feature, but just their zip code may indicate a lot of even their educational level, right? So it's very important to know your problem and try to understand your problem in depth. Now, the second part that it's much more tricky to do is in processing. So, do you know how machine learning models work? More or less? Okay, more or less. So, on average, a machine learning model will try to minimize a loss function, right? And will say, okay, the loss function may be different according to the model, but this is the general idea behind each and every one of them. What you can do here is go inside this optimization function and change it. You can do you can do different kinds of things depending on the model and the project. Not all algorithms, though, are easy to tweak. So if you have convex models, this is easier to do. If you have non-convex, much more tricky. For example, I don't know, linear regressions, and in general, the class of regressions are much more easy to go directly in the optimization function and tweak it in a way that the output can be fair. Others, like XGBoost or neural networks, are much harder. Others are impossible. So I don't know. I cannot go and change ChatGPT. I don't know. It's a black box. I don't even know what is in there. Okay, so the last one is the post-processing. And this is an intermediate way to try and work around your problems. So what this thing does is, the general idea is that you're trying to work on the output of the model. And you're trying to weight or put a logic in how the decision is made before the final choice of classes. I will continue with the example that I was showing you before. How do you go and you tweak the optimization function? There has to be a logic, right? It's not that, for example, XGBoost, the optimization rule that it has is that it measures the error, has a threshold of 50%. I say, okay, whatever is below this threshold is one class, whatever is above is another class. But if I want to change this because I don't like it, because the model is not fair, I have to say what is fair. So say what is fair, there is no answer to that. And there is no answer to that because it depends on what you're trying to build. Every single problem has its own fairness aspect. So whether I'm building a classifier that will choose whether someone has to go to death penalty or whether I have to make a classifier that chooses whether someone has to get a newsletter are two totally different problems. And not only there are two totally different problems, but the sensitivity and the precision that you require in each and every one of them, the extent to which they affect the lives and the well-being of people is totally different. So in this particular case of an assistive intervention of the task that our interest was to optimize a campaign, an advertising campaign to have more unemployed but equally represented according to their gender. In our specific case, the criterion that we wanted to optimize was the parity, the false negative rate parity, which is also called parity of opportunity. So Okay, I don't want to tire you too much. Basically, what you do is that you're setting a group of reference, usually the majority group, the males, and then you see what is the ratio with the females, your group that is the one that is being treated less fairly, let's say. And you see how much every time you benefit one or the other. Of course, the perfect ideal situation would be 1-to-1. This is usually not the case. So what you do is that you put an arbitrary threshold of 80%, and you say, okay, in 10 males, if I have 8 women, I still consider my algorithm to be quite fair. Or if I have 12 women, still is quite fair. But these are more or less, you have to have some kind of flexibility because things not necessarily work perfectly. Now, what happens is that if you estimate, okay, second arbitrary choice is the scaling factor beta. And I will I will refer you to the work of Ricardo Baeza Yates for that, because there is not a standard threshold. There is not one specific solution. It's an arbitrary. It's proven to work, but is quite arbitrary, the choice of the exact number. So basically, what is below 0 favors precision. What is below 1 favors precision. What is above 1 favors recall. And what we try to do here is that we see, okay, what happens in this threshold if I start altering the decision-making point of my XGBoost all across the scale from 0 to 1. So what I said before, XGBoost has a set threshold of 0.5. Whatever is below is one class, whatever is above is another class. What happens if this is 0.2? What happens if it's 0.3, and so on. And we find the point that maximizes this threshold. So that maximizes the fairness, let's say, the fairness ratio between males and females. And for those ones, we see that for males, the threshold should be at 0.5, and for females, 0.82 or something. Now, what happens with this thing here is that, okay, the big ugly table moment. What I told you before, the accuracy that we had was 0.74, right? And this remained invariable. This remained stable. We tried 4 different models. The first one using demographics, not using demographics, the hiding demographic model that I told you doesn't work. And then what happens if we put this different threshold to the model using the demographics and without, right? So what we see is that using the adaptive threshold in both cases, we can provide a result that keeps the same amount of accuracy, but chooses fairly between males and females. That is the ratio that goes close to 1. The trade-off for this is that you have to give up recall, right? You cannot have everything, as I told you before. So the interesting thing of this approach is that you can quite easily choose what is a fair interpretation outcome of your model and modify the choices that your model makes in the population that is chosen. But you cannot optimize for everything. You can only optimize one criterion at a time. The limitation of this approach is that although I can aggregate more than one features, and I can say, okay, I want a model that is fair both to gender and age and race and something like that, the more I add attributes, the more I go to something that is very sparse. And so I can go to identification of people. And that's an important thing to remember. You cannot optimize more than one fairness metric at a time. So, map of Italy, the usual poor south and rich north. This is an icon, an image that will pop up in almost everything that you're studying about Italy. So this is the census. This is the green part is where we have more female more unemployment, and the red part is the violet part is where we have less unemployment. And this is what happens in the models that, of course, that do not consider demographics, because we said this is something that didn't work properly. With and without the threshold that we have applied. So the more transparent the color, the more fair is the prediction in terms of gender, right? Now, this was a toy example. It never got deployed. But now I'm going to talk to you about things that are more coming from the field. So emergencies happen. As I told you before, humanitarian response is immediate, urgent. They produce a lot of documents that are all over the place. And a question that my team in UNICEF got was, okay, how can we identify automatically places from reports? Reports can come in any kind of textual forms. So we want just to parse places and geocode them and show immediately in a map where things happen and where things are located, right? Now, okay, fine. We went into built a pipeline where it would take from documents that we knew and we had annotated the locations. We would use those, annotated by experts, on what is a location, whether it's an actual location, whether it's an associative location. Associative meaning, exactly, Netherlands Red Cross. I'm not talking about Netherlands, the country. I'm talking about someone that is related to that country. And although it is a location, is not what I'm looking for in a humanitarian document, because it's not that the emergency happened in the Netherlands, but perhaps these people went somewhere else to help, right? So we did this manual labeling of the data, and then what we did is that we relied on Roberta, the BERT model. I don't know if you know it, and Spacey. Do you know it? You don't know it? Yes, no, perhaps. Okay. I see people moving it. Okay. And we relied on these big embedding models that are pre-trained usually on social media data to build our pipeline. And we use these models just to fish the location from the text. And then we use GeoNames, which is a library, a Python library that translates a name of a location into a GPS location, right? Latitude and longitude. Now, we got pretty good results. Again, as I said before, 7.5. Don't laugh. It's a very good result for for these kinds of approaches. But then, of course, we go to see what works, what doesn't work. What happened is that we noticed that many of the places were not were mismatched. So I will show you the map first. So countries with a yellow background in this image are countries from which I have documents, that I know that these documents have been authored to address a problem in those countries. The blue dots are the geolocated places that I got from Spacey reading the reports, right? And then seeing these results, we asked ourselves whether most of the humanitarian emergencies happen in the US. Well, I don't know, the current news perhaps, but this is a... So we said, okay, there is something wrong, right? There is something that that is off. It cannot be that all the humanitarian emergencies needed in New York. So what we did is that we went back and we fine-tuned Roberta and Spacey according to these annotations that we had done. And then we combined both models to see whether they work better together, because we saw that there are cases in which Roberta works better or Spacey works better. So we try to combine both and see what happens. And what we got are the red dots, which again, they're all over the place. And I cannot tell you for sure that, this red dot probably the red dot in Antarctica is also a mistake, but is more uniformly distributed in around the globe and around the places that I know that these documents come from. So it's not a solved problem, but is a little bit better than what we had before. And we were asking ourselves, okay, what did we do wrong in this pipeline? And the question, the main answer to this is that JORNAMES is a library that is mostly trained on data from the US. It's a library that is used by applications in the USA for geolocation. So the amount of data that this library has from the US and Europe with respect to the rest of the world is totally imbalanced. And the thing is that when a location has the same or similar name in two places, the default of this library will be US, because probably you're looking for the Siracusa in the US, not the Siracusa in Italy, that is much smaller, right? And the same with Santiago. There are so many Santiagos around the world. Which one are you referring to? Probably the biggest one. But in my case, probably not. And you may say, okay, but this is something that just happened once, and this happens when you're using tools for your research that are not meant to be for this scope. And of course, it was a commercial library, and this is why you had these issues. But these issues come up also when tools are made for the humanitarian domain. I don't know if you're familiar with Data for Good team of Facebook, Meta. No? They have very interesting products. So this is a team inside Meta that is focusing on creating population maps, collocation maps. They contributed a lot during COVID, for example, in disease transmission. And they also created the Relative Wealth Index, which is a really nice idea. And the outcome of this index is that it gives you for each geographical tile that is, I don't remember, like 2.5 kilometers per 2.5, I think. It gives you a relative rank of wealth within a country, right? So I cannot compare against countries. I cannot say that if Crete has an index of 1 is equivalent to Italy that has an index of 1. But I can say that within Greece, Crete has an index of 1, and I don't know, Athens has an index of 2. Relatively, they are poorer than Athens, right? So how this relative wealth index was developed is a combination of satellite images, connectivity, survey data that these people got, a neural network, quite complex neural network that then maps into onto the relative index. Now, another, as soon as this index was published in 2019, as soon as this came out, the regional, the East Asia Regional Office of UNICEF came to us and said, okay, can we use this instead of surveys or instead of census to give, to inform the benefit, the social benefit program that we have. Now, why they came up, or what is this benefit program? So the government is giving monetary benefits to the poorest strata of Indonesian population, right? And it's that 25% of households in Indonesia, they belong to this extreme poverty group. How they are finding these people and how they are distributing these benefits. It's through surveys, through census, through applications, but all these things are very slow. And they're very slow to connect. They have differences in what they consider poverty, because poverty can be monetary poverty, or it can be that you don't have a car, or your house is made of one material rather than another. What is considered poverty is not exactly the same in all the ways that poverty is monitored, right? And the biggest problem is that these things are happening, these surveys are happening in moments in time. They give you snapshots in time with a different spatial aggregation, because some aggregate in admin level 2, I don't know, like a region, others aggregate in district to maintain anonymity of people. So the ground truth is messy, and I don't want to go into how much we struggled to make something that was as uniform as possible. But once we did that, we saw what is the difference between targeting with the surveys or targeting with a relative wealth index. And again, we had a pretty good correlation, both in terms of population and spatial resolution. Of course, in the maps, you see differences in color. So, the more yellow a place is, the more it has, it should be eligible for the support system. And you already see differences in the Big Island, for example, that you have a darker version with a survey and a lighter version with a relative wealth index. So, okay, there are errors, okay. But overall, if we would just look at the general correlations, they would have been decent. But this is not good enough to say, okay, I feel confident to give you a model and to give you information on something that, people will or will not get a benefit that may be crucial for them, right? So we dived a little bit deeper into what is happening, and what we saw is that if you rank the population by income, most of the errors that we do are in the lower strata of the population, are in the lower socioeconomic strata of the population. So where basically people have more need of this benefit, this is where our error is higher, and so much higher to be 50% off, right? And so this was enough to convince UNICEF, that talks to the government, and say, okay, don't use this to inform your system. Of course, it's not that governments issue benefits like that, but they take information from different sources. So this would have been one more argument to say, yes, you deserve it or you do not deserve it. So it's not that by giving this information out, it immediately gets deployed and people do what I say, but it's a piece of information that contributes to the general idea that they are forming. So I would go out and say that is something that is reasonable, whether looking into the population that is really in need, we see that we are 50% off, which is a lot. Now, why this happened? Because you may say, it's an index that is built by a major company, and the engineers of Met are for sure brilliant people. Why did this happen? Why are they so much off? They are so much off because there may be issues like the ones I mentioned in the beginning. So in the poorer places of the globe, you may not have connectivity. You may be even this mega company with coverage that has huge penetration in most of the countries of the world, they still lack visibility of people in need, right? Then it's also the fact that they trained a model in 2019 with surveys of 2019, and this is something that we did several years later. So the same problems of surveying latency hold. But the most important thing is that they as well don't have the visibility of all the population in need because of limitations of technology, right? Now, okay, at this point you should say, okay, so nothing works. Okay, and everything that we may do is problematic and perhaps is not useful or anything. So partially yes, but I will give you an example of something that is deployed and is actually out there, despite the problems. So another question that we got from OCHA this time. UN OCHA is the UN agency that is responsible for allocating resources when an emergency happens. So their question was, how can we know in advance the impact of a tropical typhoon so that we can better prepare the resources, not only the monetary ones, but also the physical ones, right? And they came to us with a basic, this is the, tropical cyclones have different names according to the area where they're in, but more or less we are talking always about the same thing, right? So what is happening now is that what was happening, and several countries still do it, is that they are relying on the error cone of a hurricane to estimate how many people may be exposed to this hurricane. So what this means is that when the hurricane is approaching, you cannot predict the path. It's a chaotic system, but you can predict more or less where it's going to hit with an angle, right? The further away the hurricane is, the more people it impacts, right? I mean, if it's further away. So the question of OCHA could not be answered like this, because when the typhoon still needs several thousand kilometers to hit the land, the cone may be covering the whole country. So for this type of approach was not necessary. So they came to us with a model that they had built, trying to predict the impact in houses. So how many houses would get destroyed? And we helped them improve it a little bit, including different feature selection, evaluation, cross-validation, and so on. And we proposed a model that was better than the one that they were using for the Philippines. And again, we noticed that, yes, overall our model was better. However, when the impact is high, the error is the highest. And again, why this happens? Because these are very rare events, and we don't have enough information to train the models on. But again, this is a little bit the distribution of the areas that are getting hit, and you see that most of the impact is low, and then you have very few rare events on the high parts of the population. Now, nice example. You have the actual damage and the path of the typhoon. You have the ones that we are predicting, and the difference, the last figure is the difference between over and under prediction. And basically our model is not amazing, but it predicts 35 out of 41 impacted regencies, municipalities, while the previous one was impacting 25. It's not great. But if we say that on average, the money that OCHA has to pre-allocate is about $150,000, we are talking for €500,000. And these are not dollars that OCHA will save, but they will reallocate it in people that are more in need, right? Now, what are the limitations of this approach apart from the fact that we don't have enough extreme events to train our models on? Another very, very important limitation is the ground truth that, to say the least, at times is questionable. So here is the path of the typhoon, and the red dots are where I am being said, this is the country of Vietnam, I am being said that the impact has happened. I don't know. For me, it's weird that I have impact all over the country. So I don't know how this data have been collected. I don't know what they mean by impacted. They may be impacted severely or not, but it's really weird visualization of impact for that specific hurricane. So at times this is as much as you can do with the data that you have, right? That said, this is deployed in many countries where the model is stable, and we're trying to make it a global model. Now, the most difficult project of all, and my favorite one, is on a totally different topic, and it's on vaccination. Vaccination in Africa. So what happens here is very interesting. So we have countries that 1 out of 10 children don't reach the age of 5. And there are a lot of them, right? And the weird part and the difficult part for agencies like UNICEF is that the official data, the administrative data, have errors and have inconsistencies. And what this means is that you may have an estimation of the World Health Organization, and then you may have government estimates that at times go beyond 100%. So this may be an impact of, I don't know, undocumented migration or populations that are floating between countries, or it may be due to other reasons. In any case, the important thing for UNICEF is that this type of information are not actionable. So when people go in the field and they want to vaccinate children, they may arrive with a huge load of vaccines that will go to waste if there is no one in need there. Or the other way around, they will reach places that are supposed to be totally covered with no vaccines, and they will find out that the reality is different. In both cases, there is waste of resources, and the question is what we can do about that, right? So this is a project in collaboration with WordPop, and what we are trying to do is we are trying to improve the coverage of vaccination. The whole idea is that if we have population estimations and coverage estimations, then we can overlay the two, multiply them, and reach a map of where are the zero-dose children. Now, the problem of this thing is that, okay, admin data are out of the question, but what we rely on are, again, surveys, covariate spatial covariates, and these models are usually Bayesian, which means that you have confident probabilities of error that get multiplied once you overlay the products, right? And you have many different products. There is not just WordPop creating population estimations. There is Meta, what I told you before. There is Grid, there is Copernicus. All very valid players. Not all models are built in the same idea. Some of them are top-down, some of them are bottom-up. The important thing is that when we use them in action, what is happening is that there are discrepancies. And what we want to arrive at is a solution that is not country per country case, but something that we can apply globally and something that is consistent with the WHO. So what we need to do is that we need to understand the sources of the variability, to compare the models and see how much variability we have per case. and to see what we can do for operational aspects of UNICEF. Now, again, the visualization, the pipeline of this comparison is that we are changing every time the vaccination coverage with a population layer and an administrative map to see the locations where these children live. Let's say that we keep the population stable. If we just vary the vaccination product that we are having, we see discrepancies that can range to 1 million children. And I mean, apart from highlighting them and showing that there is a steady systematic discrepancy between these products, there is not much more that we can do up to that point. What we are doing and what we're trying to do with this project of Reached and Enriched is that we are trying to work together with WorldPop and inform their Bayesian models. So when we see a lot of discrepancy, how we can feed back to the models of WorldPop and say, okay, in fact, you told me that in that area, I should find 10 children, but I don't know, I see 0 or I see 100, and how we can feedback this loop and make models more representative of the population. Because even increasing 1% of coverage in a vaccination estimation like this one can be translated in thousands of deaths and thousands of lives saved. So again, it's not an accuracy that you will see in a paper, and I don't know if there will be a paper out of this, but the importance of this work is that you actually have people's lives at stake. So, I don't know, a few things for you to remember for your future projects, if they are in this area, if they impact people in one way or another. Just remember that as engineers, we love to say, oh, it works. My job is done. I'm going to the next project. It may work, but it may also have a lot of blind spots that you may or you may not be able to solve, but at least you should highlight. And this is our part of responsibility in this game. The other part of contribution is on the data, of course. I mean, if not us, who is more capable to work with issues of data and issues of models and methods. A very tricky part is how we communicate those. So how I speak to you or how I speak to a humanitarian person that is in the field is totally different. And how I'm going to explain to you what is a probabilistic model and how I'm going to explain to them what is a probabilistic model is totally different. And you have to learn a little bit how to communicate with different stakeholders to push your projects and transform them from something that is a very interesting thesis and a very interesting project to something that is actionable. And that's it. That's all from me. Thank you.